there, this video is on section 2.4, and I realized that I had forgotten to put the title in this section, which is the real zeros of a polynomial function. So in this class, identifying the real zeros of a polynomial function, so those values that would make the function value equal to 0, can be helpful for us when we're trying to sketch the graph of a polynomial function, right? Because those real zeros end up corresponding to the x-intercepts of the graph. And from there, that along with end behavior, that can give us an idea of what the sketch of the graph of a polynomial function looks like. There's other situations that we'll come upon where it will be useful finding the values that would make a function's output 0 this year as well as next year. So just kind of another skill that we are adding to our toolbox. So in order to help us with identifying the real zeros of a polynomial function, we're going to use something called the remainder theorem. So the remainder theorem says that if a polynomial p of x is divided by x minus a, so linear divisor x minus a, then the remainder will be equal to the polynomial evaluated at a. So the remainder will end up being equal to p of a. This theorem tells you that that polynomial division can be used to evaluate a polynomial function at a particular point. And you're maybe like, well, why would I do that if I could just plug the value in? Well, the remainder theorem is kind of the basis for another theorem that's going to help us more with identifying the zeros, the real zeros of a polynomial function. So bear with me for a sec. Let's look at this example to demonstrate the remainder theorem. So if we're given p of x is x cubed minus 2x plus 4, find p of 1 by dividing p of x by x minus 1. Then confirm your answer using direct substitution. So we'll confirm that we get the correct value of p of 1 by dividing x cubed minus 2x plus 4 by x minus 1 to make sure that the remainder matches that value. So since we are dividing by x minus 1, we can use synthetic division here. We don't have to do, you can use polynomial long division if you prefer, but I'm going to use synthetic division. So that would be putting the 1 there, and then the coefficients of p of x, so 1, I'm putting a 0 there as a placeholder for the x squared term, minus 2, 4, bring the 1 down, 1 times 1 is 1, add straight down, we get 1. 1 times 1 is 1, and then negative 2 plus 1 would be negative 1. Negative 1 times 1 would be negative 1. And then when we add straight down, this column, last column is always our remainder, we will get 3. So this means that we believe, based on the remainder theorem, p of 1 would be equal to 3. And we can check that out. So p of 1, let's see if this is true by direct substitution, right? So p of 1 would be 1 cubed minus 2 times 1 plus 4. So 1 minus 2 would be negative 1 plus 4 would be, what do you know? 3. Okay, so when we divided our polynomial by x minus 1, we ended up with the value of p of 1. So this leads us to the factor theorem. And we need the remainder theorem in order for factor theorem to exist. And factor theorem is more useful to us, where it basically says if p of a is equal to 0, then x minus a is a factor of p of x. But also if the reverse, if x minus a is a factor of p of x, then p of a would be equal to 0. So this is really helpful for us. If x minus a is a factor of p of x, then its remainder, whenever you divide x minus a into p of x, should be 0. and therefore that helps us with factoring. That helps us with identifying the zeros. So let's give it a try. Let's apply factor theorem here. So let's determine whether x minus 1 is a factor of h of x. Okay, and we can do that by first, we could think about evaluating h of 1. That's our first option. Or that's what factor theorem says, right? So if h of 1 is equal to 0, then x minus 1, that means is a factor. That doesn't tell us what what times x minus 1 would be equal to h of x. You have to actually do the division. But it is helpful to know that x minus 1 is a factor and 1 is a 0. If it is, in fact, our remainder ends up being 0. Or h of 1 ends up being 0. So 1 cubed minus 4 times 1 squared minus 7 times 1 plus 10. So 1 minus 4 would be negative 3, minus 7 would be negative 10, plus 10 would end up giving us 0. Okay, so that means that 0 is the remainder of x cubed minus 4x squared minus 7x plus 10 divided by x minus 1. And that's useful to us because if we were trying to factor h of x, we would know that x minus 1 is a factor of h of x. So we could say, therefore, x minus 1 is a factor of h of x. Okay, because when we evaluate h of 1, we get 0. That means that 1 is a 0 of h of x. Therefore, x minus 1 is a factor of h of x by the factor theorem. Now, if we wanted to go a little bit further than what this question is asking, we could. We could actually do the polynomial division. So we could use synthetic division here, right? In order to see what times x minus 1 would give us h of x. Because then we're on the road to factoring. So using synthetic division, so putting all of the coefficients of h of x there. I don't need any placeholders. I can bring the 1 down. 1 times 1 is 1. Negative 4 plus 1 would be negative 3. Adding straight down. That last column is our remainder column, and we get our remainder of 0, which is what we expected. So that means that another way to write h of x would be x minus 1 times x squared minus 3x minus 10. Right? This would be x squared minus 3x minus 10. And then if that quadratic is factorable, which it is, minus 5 plus 2, then there we go. We've factored h of x completely over the real numbers. We have h of x written as a product of linear factors, which then from there we could identify the zeros, which correspond to our x-intercepts of h of x. But we've already answered the question. We know x minus 1 is a factor of h of x. Okay, so now, still using factor theorem, determine whether x minus 3 and x plus 2 are factors of k of x. And if they are, factor k of x completely over the real numbers. I mean, k of x is a quartic. We don't really have another starting point unless we're given a potential factor of trying to factor this quartic. So this is kind of our jump start, and there's two different methods based on the factor theorem. So our first method, I'll call this method 1. This is my non-preferred method just because I think method 2 kills 2 birds with 1 stone. But first method would be determining whether or not 3 and -2 are zeros of k, which would then mean that x minus 3 and x plus 2 would be factors. So k of 3 that ends up being 0. So yes, x minus 3 is a factor of k of x. And then k of -2 is also equal to 0. Okay, so what that tells us at this point is that k of x can be written as x minus 3 times x plus 2 times something. We don't know what that something is, though. But what we could do is, since we know our equation of k of x, and we know that since x minus 3 and x plus 2 are both factors of k of x, if we multiply them out, we can then divide k of x by that x minus 3 and x plus 2 multiplied out, and that would give us our remaining factor. So we'd have to do polynomial long division for that. Now if we multiply x minus 3 and x plus 2, we get x squared plus 2x minus 3x, so minus x minus 6. We are trying to find this remaining factor here. So we're going to divide k of x by x squared minus x minus 6, because we know that x minus 3 and x plus 2 are both factors, therefore their product would also be a factor of k of x. So k of x is x to the 4th minus x cubed minus 7x squared plus x plus 6. I don't need any placeholder. So then I think, okay, well, what times x squared would give us x to the 4th? And that would be x squared. Distributing minus x cubed minus 6x squared, and subtracting, as that would end up being 0, so negative 7x squared, so that's x squared, right? And then bring the plus x down. We could bring the plus 6 down too if we want. But then we go, well, what times x squared would give us, I'll bring the plus 6 down as well. What times x squared would give us x squared? That would be plus 1. Oh no, that should be minus x squared, huh? Sorry, negative 7x squared plus 6x squared would be negative x squared. So that would be minus 1. And then distributing. Oh, well, that works out nicely. Our remainder is 0. So that means that x, we were expecting that, x squared minus 1 is that remaining factor. And we know what x squared minus 1 factors to, right? So k of x in completely factored over the real numbers is x minus 3 times x plus 2, and then x squared minus 1 is the difference of 2 squared, so x minus 1 times x plus 1. So that's method 1 of factoring k of x over the real numbers. Method 2, draw a line here. We'll use a different color. So method 2, I would prefer, because I just think it's killing two birds with one stone. So by the remainder theorem, right, factor theorem, if x minus 3 is a factor, or 3 is a 0 of k, then it should divide evenly into k of x. So I'm just going to go straight to using synthetic division. So put the 3 and then all of the coefficients. Bring the 1 down. 1 times 3 is 3. Add straight down. 2 times 3 is 6. Add straight down. Multiply. Add straight down. And we get negative 6 in the last column, which is our remainder column. We get a remainder of 0. So again, that shows us x minus 3 is a factor. But that means that k of x can be written as x minus 3 times, but this would be x cubed plus 2x squared minus x minus 2. And then we can just keep going because we need that to factor further. So we also want to see if x plus 2 is a factor. So then I'm just going to draw my little box here for synthetic division. I'm going to put negative 2 here, bring the 1 down. 1 times negative 2 is negative 2, add straight down. And 2. And then sure enough, we get the x squared minus 1. And we got the remainder of 0 whenever we divided the x plus 2 into that factor of k of x. And this would allow us to go through those same last steps of saying, okay, well, k of x is equal to x minus 3 times x plus 2 times x squared minus 1, which again, you guys know, difference of 2 squares, that factors to x minus 1 times x plus 1. So just a little, I think that's a faster method. And if you got a remainder for either of those values, they would not be zeros, therefore they would not be factors of k of x. And then you'd be kind of stuck, at least for now. So the number of real zeros for a polynomial function can't be more than its degree. And I want to, so this is the way it's written in the book, but I feel like it should actually state a polynomial function cannot have more distinct real zeros than its degree. And that goes back to multiplicity, right? So you can think of a degree occurring, or sorry, a 0 occurring more than once. If you have it, the multiplicity is whatever x minus a to whatever the power is that it's raised to, that's its multiplicity. So you can think about a 0 as occurring more than one time. So you could have the same number of distinct real zeros as the degree of the polynomial. You might have a 6-degree polynomial, though, where there's only one real 0 and no complex zeros, right? Like if you had x minus 1 to the 6th power, 1 would be your only 0, and it would have a multiplicity of 6. So that's helpful for us. That kind of gives us some parameters or some guidance on how to factor a polynomial and identify its real zeros. The next theorem is going to be the most helpful to us, though, and we're kind of putting the other theorems together in order to help us with factoring a polynomial completely over the real numbers and therefore identifying its real zeros. The rational zero theorem, aka the rational root theorem in different texts, says that if a polynomial function p of x has integer coefficients, then every rational zero, not necessarily irrational, but every rational zero of p of x will be in the form of plus or minus. You take the positive factors of the constant over the positive factors of the leading coefficient. So they'll be in that form. And that just goes back to, if you think about how guess and check works for factoring a quadratic, it goes back to that. But you're welcome to, I believe the text has a more formal proof of it. So every rational zero of p of x, remember a rational number can be written in the form of a over b. So every rational zero can be in the form of plus or minus one of the factors of the constant term over one of the factors of the leading coefficient. So this basically, rational zero theorem, gives us a potential list, helps us with coming up with a potential list of possible zeros of a polynomial. Now, from this list, you could find all of the rational zeros, or none of them could be a zero of the polynomial, right? You could have a polynomial with all complex zeros, so numbers in the form a plus bi, which we'll talk about in section 2.5, or all irrational zeros, or so, although I guess, yeah, so it really gives us kind of a starting point. And then we're putting this together with our factor theorem in order to help us determine what the actual real zeros of the polynomial are. Okay, so we want to factor g of x over the real numbers. Okay, so our starting point is going to be to list all of the possible rational zeros based on rational zero theorem. So we're going to focus on, what colors did I use? The factors of -3. And then the factors of, this one's not very interesting, of 1, right? Because this polynomial has a leading coefficient of 1. Okay, so all of our possible rational zeros can be listed as plus or minus. The factors of -3 would be 1 and 3. And then the factors of our leading coefficient, 1 is just 1. So the different combos that we're going to have are 1 over 1, so plus or minus 1, and then plus or minus 3. So we're going to need to test to see if positive 1, negative 1, positive 3, negative 3 are zeros of g of x. And if we use synthetic division along the way, that'll also help us with factoring the polynomial. And it's kind of just a guess. You may come up with your own strategy. Like testing 1 or -1 is a good start. So I'm going to try testing, but it's a little bit of a guessing game. Just like guess and check until you've practiced and gotten good at it, or more familiar with it. It's a little bit of a guessing game. So starting with, I'm going to start with positive 1. Okay, I'm using synthetic division to test whether or not x minus 1 is a factor of g of x which in other words, whether 1 is a 0 of g. So putting the coefficients of g, bring 1 down. 1 times 1 is 1. Add straight down. 3 times 1 is 3. Add straight down. 1 times 1 is 1. Add straight down. Okay, and oop, we got lucky. Okay, so this one worked. X minus 1, that means, is going to be a factor. Now, you can have repeated zeros, right? You can have a 0 with a multiplicity more than 1. So we could test 1 again. We could. So why don't I try that really fast? So if we test 1 again, bring the 1 down. I don't think this is going to work. Not feeling good about it. Nope. Our remainder ends up being 8. Nope. But what we know right now is that g of x can be written as x minus 1 times x, what is that, x, oops, x cubed plus 3x squared plus x plus 3. And then, oh, you might notice, hey, I could finish factoring by grouping, or you can continue on using synthetic division. So, like, I think you could, again, use grouping. So I think I'm going to try -3. So then using synthetic division, or you could factor by grouping, that's fine too. Put those coefficients of that factor we're trying to factor there. Because if x plus 3 is a factor, then it should divide into that remaining factor. So bringing the 1 down, 1 times -3 is -3. Oh my goodness, it worked. Okay, so that means x plus 3 is a factor, and then that remaining factor is x squared plus 1, which does not factor over the real numbers. Okay, does not factor over the real numbers. So we're done. We've finished x squared. So just to demonstrate that, right? If we were to set x squared plus 1 equal to 0, right? Because if it's a factor, then we should be able to identify the zeros for g of x there. So if we set that equal to 0, we'd get x squared equals to -1. And then, that would mean x is equal to plus or minus the square root of -1, which is the square, or which is I, right? The imaginary number. So not factorable over the real numbers, you're done. We're only in the real numbers in this section. Okay, let's try factoring the function w of x over the real numbers. So let's start with our rational root theorem. So our factors of 6 would be 1, 2, 3, and 6. And then factors of the leading coefficient 3 would be 1 and 3. So we're going to have to test plus or minus, 1, plus or minus. You can just put the plus or minus up front if you want with the list, or you can put with each possible rational 0. But we'd have plus or minus 1/3, plus or minus 2, plus or minus 2/3, plus or minus 3, plus or minus, well, 3 over 3 would be 1, so we don't need to do that again. Plus or minus 6, plus or minus 2, which is already on that list. Okay. Okay. So I think I'm going to start with -1. So I'm going to do synthetic division. Or I'm going to start with, positive 1. So I'm going to do synthetic division. 3, -5, -17, 13, just putting all the factors there of w of x. Bring the 3 down. 3 times 1 is 3. Add straight down. We get -2. So what would that be? -19. And that would be -6. And oh my goodness, did I get lucky? Okay. So you could try testing 1 again. I don't want to. I want to try -2. I want to try -2. Okay, bringing the 3 down. So that would be -6. That would be 16. And then +6. What do you know? It works. Okay, and then now we're down to, that's a quadratic factor, which you could factor using guess and check. So we'd get w of x is x minus 1 times x plus 2 times 3x squared minus 8x minus 3. And we can see if that factors, which I believe it does. So 3x x. So that would have to be minus 3 plus 1, like so. Yep, that works. Now I do want to point out one thing. If you had not used guess and check, or let's say that you had tested -1/3. So if you tested -1/3, okay, 3 times -1/3 would be -1. So it would be -9 times, so that would be 3. Well, I guess it actually works out okay for this one. But let's say that you had tested -1/3 earlier, and you just test the 0. So you test like -1/3, and then maybe the 1, -2, and +3, where you just identify the zeros from doing synthetic division, right? You see that you get remainders of 0 for all of those. My point in kind of going back over this is you need to make sure that if you were to multiply out all the factors, that you would get the original polynomial, which has the leading coefficient of 3. And if you just identified the zeros and then took all the zeros to write your factors of the polynomial, you would have like x plus 1/3, x minus 1, x plus 2, x minus 3, and that multiplied out would have a leading coefficient of x, a leading coefficient of 1. So you just need to be careful. You need to make sure that that leading coefficient is there. It worked out fine here, But like if you had kept going the way that I said this, then you would have had x plus 1/3, and then this last factor would have been 3x minus 9, and that's fine too. You just need to make sure that if it were to be multiplied out, the leading coefficient would be there. Okay, so now we're gonna factor completely. So we're gonna put what we've been talking about in the last two sections all together in order to sketch the graph of this polynomial. So we're going to figure out what the x-intercepts are by identifying the real zeros of the polynomial using rational root theorem, because this cubic can't be factored by no guess and check and no grouping. So we'll use rational root theorem to get us started. We'll find our x-intercepts, their multiplicities, and we'll talk about end behavior and then do a sketch of the graph. So first, thinking rational root theorem, factors of 6 would be 1, 2, 3, 6. And then the leading coefficient is just 1. So that's all of our possible, you can just reference that list actually. I'm going to start with 1. So putting the coefficients there for our synthetic division, bring the 1 down. 1 times 1 is 1. -5. What that would be, +6. What do you know, it works. Okay, and then, so that means x minus 1 times this quadratic would be f of x. So f of x can be written as x minus 1 times x squared minus 5x plus 6, which is x minus 3x minus 2. Okay, so our real zeros with their multiplicities would be 1 with a mult 1, 3 also mult 1, 2 also mult 1. And our x-intercepts then are 1, 0, 3, 0, and 2, 0. And then the graph, because each of those has a multiplicity of 1, the graph will end up crossing straight through each of those points like a line. And then let's think end behavior. And remember, when we think end behavior, we think, okay, as x approaches negative infinity, what is f of x? What are the y values going to approach? And we can focus in on just the term with the largest exponent. And since it's x cubed, you can think about x cubes and behavior. You're familiar with that. Or since it's an odd degree with a positive leading coefficient, the end behavior would be like a line with a positive slope. So as x approaches negative infinity, f of x would approach negative infinity. And as x approaches positive infinity, f of x would approach positive infinity. So then sketching the graph. Remember, it's a sketch. Oh, we only have positive x-intercepts. Okay, so 1, 2, 3. Oh, that's all I need. Oops. Okay, so plotting those point, the x-intercepts, 1, 0, 2, 0, and 3, 0. Knowing end behavior, okay, to negative infinity, to positive infinity, and the fact that the graph crosses straight through, it'll look something like that. Without calculus, we don't know, I'm not making you do test values. Without calculus, we don't know how high in between or how low in between the x-intercepts the graph goes. So this is just a rough sketch of f of x. Okay, and we'll do one more sketching the graph. So identifying our x-intercepts. I guess we could have identified, our y-intercept for this one. Our y-intercept would have been 0, -6. So we could have plotted that. Okay. Okay, so first let's think possible irrational zeros. Ooh, this is going to be kind of a long list. Plus or minus factors of 15. 1, 3, 5, 15, and then for 2, 1 and 2. But that means we have plus or minus 1, plus or minus 1/2, plus or minus 3, plus or minus 3/2, plus or minus 5, plus or minus 5/2, plus or minus 15, and plus or minus 15/2. I'm going to try -1 first. And because there are so many, and I don't want to, so many possible rational zeros, and I don't want to get to the end of the list and none of them have worked, and then have to retest. Once I get a 0, I'm going to retest it just to see if it has a multiplicity larger than 1. So putting the coefficients of j of x here. Okay, and that worked. I can't factor that with a grouping or guess and check. So I'm going to test -1 again. And that might just be a strategy that you use. Once you get a 0, a rational 0, test it again. You don't have to. It's just something that might be helpful. Oh, what do you know? It worked. Okay, and then we have a quadratic factor. So I'm almost done. Okay, so that means that j of x can be written as x plus 1 squared times 2x squared plus 7x minus 15. Let's see if that can be factored using guess and check. Yep. So 2x minus 3x plus 5. So that means that our zeros are our real zeros, if we want to be extra specific, are -1, which has a mult of 2. 3/2 has a mult of 1, and -5 has a mult of 1 as well. So for our x-intercepts, -1, 0 is just going to touch the x-axis. 3/2, comma 0 will cross like a line. And then -5, comma 0 will also cross like a line. So cross straight through. And then for end behavior, as x approaches negative infinity, j of x will approach. We can focus on 2x to the 4th, which even degree, positive leading coefficient means both ends pointing up like a parabola. So we'll approach positive infinity, and then same thing as x approaches positive infinity, j of x will also approach positive infinity, right? So both ends up. -15 is the y-intercept. Okay, let's see. Okay, so let's graph the intercepts. Both ends up. So as x approaches positive or negative infinity, the function's approaching positive infinity. It'll come down and touch at -1, and then a y-intercept of -15. I'm just going to make this go down a little bit further. We'll just estimate. Let's just say -15 is down here. This is just a sketch. So it'll come down, maybe cross. Maybe that's the lowest point. Maybe it's not. We don't know. So it'll look something like that. You could always compare on Desmos. Do I have it there? I think that's a different one. Oh. I feel like it's always somewhat satisfying if I get my sketch to look somewhat like what the graph actually looks like. Okay, I think we did well, no, so the minimum value is actually in between -5 and -1, but that's okay. We would need calculus to identify that lowest point, or you could do a lot more test values to get a more accurate picture, but this is fine. So in reality, this part goes lower, significantly lower. Okay.